I almost feel guilty because it looks like I just copied the calendar down, the list of topics, right? But that's not what I did. I actually looked at an old exam that's pretty in line with what I plan on giving you. And so let's just talk about this first, all right? And then we'll get to today's stuff. You need to be able to evaluate limits, all right? 0 to 0, that's the first type we ever saw. You know, use some sort of algebra, factoring, conjugate, something like that. And I say just be prepared for that, right? You know, remember what happens when you have fixed over 0. You have to draw a number line, figure out, you know, is it positive or negative infinity? Anytime you have infinity over infinity, what do you do? Or if you have other indeterminate forms, you might use a natural log, or you might use L'Hopital's rule. Then I will have one problem on the test. It won't be complicated, but it'll just make sure that you know how to use the limit definition to find the derivative. That's that, you know, limit h goes to 0, f of x plus h minus f of x all over h. That formula that we like threw away as soon as we got the shortcut rules. You'll have to do that at least, well, there will be one problem. Find the equation of tangent line. So that right there, find the equation of tangent line. At that point, well, at any point in the test when I ask you to take derivative, you always want to use the shortcuts, right? All the rules, except for that one problem where I will say use the limit definition, all right? Otherwise, like for the next one, find the equation tangent line, you just take your derivative, you use your point to find your slope and all that, and come up with the equation. Of course, you have to know how to differentiate, right? All the rules. You need to know how to use implicit differentiation. So that's like, you know, dy dx, blah, blah, blah. And with that, be able to find an equation of a tangent line. A very basic related rate problem. So, you know, a circle is expanding so that its radius is increasing at a constant rate, blah, blah, blah. You know, something very basic shape. It's not going to be one of the more difficult problems, but you need to demonstrate that you know how to go through drawing a general picture, instant in time, all that. We're talking about the final. Then derivatives of logs and exponential functions. So just make sure you know how to take derivatives of those types of things and how to apply the chain rule to them. Finding the global max and min on a closed interval, so the closed interval method. I'm not going to have you graph anything in this test, but I will have you do that one where it says find where functions increasing, decreasing, local max, local min, concave up, concave down, inflections. That's basically almost all of the work for graphing, at least all of the calculus work. You'll still have to do that, but you won't have to graph anything. Find antiderivative using knowledge of calculus derivatives. So that's basically what we did last class. You know, like what's the antiderivative of cosine of x? Well, we know that from Cal 1, so it's sine x plus a constant, right? And then find the antiderivative using the power rule and U substitution. U sub, we have not talked about. We're going to do that today. And then the last part will be finding a definite integral, which we will talk about either today or next class. All right? Okay. Add to this, I didn't put it on here. Please add to that. I forgot to put logarithmic differentiation. So that was on your last test where you're trying to take the derivative of a function where you've got x's both in the base and in the exponent. And so you have to come in and take log on both sides and then differentiate. So, you know, and there was another problem on the test where it was like something cubed times something real nasty over something nasty. And if you try and take the derivative, it's real ugly, but if you do logarithmic differentiation, it becomes a lot easier. So those are the two types of problems you could see with logarithmic differentiation. Okay, any questions on that? The final is on Thursday. Yeah, Thursday. And I believe it's at 12:30. So it's not at 1. That's not my choice. That's the way they do it. So 12:30 to 3:15. And I would say, you know, expect to be here the whole time. I'm not going to say that it's going to take you the whole time, but, you know, someone's going to take the whole time for the test, so I don't know if that'll be you or not. Any questions or anything?
So Newton's method won't be on the test?
Newton's method will not be on the test, no. And that again was just, I showed you Newton's method to let you see how we can find solutions to equations using calculus and how computers do it, right?
Wait, how did our final get moved to Thursday? I thought we would have a top of the hour class if Thursday makes sense.
They normally do. Well, no, I don't think it's. I can double check it, but I'm pretty sure. Pretty sure it's.
Tuesday's off. Tuesday when I have a class.
Well, it's these hour 40-minute classes get scheduled differently, because the hour 15, those hour 15 classes, they can do those on certain days, but then on these they'll overlap.
Yeah.
So they have. That's why we start at 12:30. So I'll double check it, but I'm pretty sure it's right. Okay. All right, so last class we were talking about antiderivatives, right? And every time I wanted you to find the antiderivative of something, I kept on writing on the board, find the antiderivative, right? Find the antiderivative, find the antiderivative. So now we have some new notation.
Professor, do you want this quick thing?
Sure. If you want to turn it in. Which one is this? Oh, going back and getting the C's? The C and the D's in the function? I forgot about this. I knew I gave a class a take-home quiz. I couldn't remember in what class. Here we go. Here we go. Was that pretty straightforward, this thing?
If I did it right, it wasn't hard.
Yeah, okay, good. Well, remember you can always check your answer, right?
Yeah.
And then you could use the given information. Anyone else? All right. So we're gonna have some new notation, all right? And the notation is gonna look really weird, but I will try and explain it to you, if not at the end of class today, next class, where the notation comes from. Right now, I just want you to be like, okay, it's just new notation. So you know how when we wanted to take, I'm going to just put this on the side here. When we had a function, if we wanted to take the derivative, right, then we would just do that, and the notation was just that little symbol, and it was very nice, right? But if we want to start with the function and find its antiderivative, the notation looks like this. Okay, so imagine that that's like an S that's been stretched out, okay? And then what you do is you put the function here, and then right next to the function, and this is really multiplication, is this little thing dx. So this is the notation, all right? I'll explain what everything, or I'll name everything. This right here, I'll do a different color. This right here is called the integral sign. Okay. The function that you put in here is called the integrand. That may look somewhat familiar if you go back and remember radicals? The thing inside the radical is called the radicand. Well, the thing inside the integral sign, or next to the integral sign, is called the integrand. And this little thing right here, which seems really strange, is called the differential. Now the differential is the part of the notation that's the most confusing to students. So this just says, that when you see this symbol in front of a function like this, this is telling you to find the antiderivative, all right? Find the antiderivative of that function. This right here, until I can explain where it comes from, is going to just look weird. Right now, just look at it as this thing that keeps track of what our variable is, okay? That's what it is. It keeps track of what our variable is. All right. So let's do an example, because we had a whole, Thanksgiving weekend. Okay, so as an example, if we write that down, right? That's asking you to find the antiderivative of x cubed, right? So what is our answer? 1/4 x to the 4th plus a constant. So I'm using the rule that we established last class. That was if we ever had x to a power, then to find the antiderivative, we just add 1 to the power, put it up here, and then we divide by that same power, so 1 over that. Now, I heard someone say, maybe I did, maybe I didn't, x to the 4th over 4 plus c. These are the same answers, okay? The reason I don't do this is just because in calculus, the number out front always just like comes along for the ride, or like if we take the derivative, this number comes out. And so I just like to leave all constants out in front of the variables. That's just my preference, but they're the same thing, yes.
So this is the area of x cubed, x to the 4th?
Not, yes and no. It is going to have something to do with the area underneath that curve, but right now you wouldn't know where to look, right? Because x cubed goes in both directions forever. So I'd have to like tell you to look in some certain window.
This is indefinite integral, right?
This is what we call an indefinite integral, yep, which is exactly the next thing I was going to say, yes.
But had you put like 4 or something as your constant, then you would have an area at a specific location, right?
Over here?
Yeah.
If I put an actual number here, we would still just have a function. It would just be, this would just be some new function, right?
Are we ignoring the dx? You said?
Okay, I'm glad you asked. The question was, do we just ignore the dx? Yes. I mean, this has nothing to do with anything. Well, it does, but right now it doesn't. What it does, but it doesn't, okay? So a lot of students have trouble with this, and they're like, where did the dx go, right? Like, where is that in the answer? So if this helps you, even though it's like completely not right, the dx just turns into the c. And maybe that'll help you not forget your c. Okay? Really, it's this, though. Find the antiderivative of that function. All right? Anything else? All right. So that's, I mean, we could go and do more antiderivatives now, but should I do more examples, get us warmed up, or are y'all ready to go into the new topic? Ready to go? Okay. So now, let's take a look at an example. All right. So if I had written on the board cosine of x, what would everyone say the answer to this would be? Sine x plus c, right? So this is not cosine of x, it's cosine of 3x, right? So what do you think maybe the antiderivative is? Let's just go for it. Let's just take a shot at this.
I feel like there's some sort of change.
So maybe it's sine 3x, right? I mean, that seems natural that you might think it's just sine 3x plus a constant, right? But what's wrong with this? Yeah, because look, the whole idea is if this is the antiderivative of this, then when I take the derivative of this, I better get this, right? So what happens if I take derivative of this? I get cosine of 3x, good, right? But then chain rule says times the 3, and this didn't have a 3, did it? It didn't have a 3. Yes?
Would it be 1/3 of sine?
1/3 of sine of 3x would have worked, right? So we need to have that 1/3 out here to account for the 3 that's going to pop out when we do chain rule, right? So now if I change this and I would have put 1/3 here, now it works. Do y'all see that? Now it works, because now if I take derivative of this, I have 1/3 cosine of 3x times derivative of what's inside, which is 3, and then these 3's would cancel, and you'd be left with with that and they match, right? So I guess the point is there's a little more involved here. Yes?
Can you formulate, like, can you like explain more of the, like, how would we know to look at it and say, okay, well, I know it's got to be 1/3
Because the derivative of 3x is 3. Right? So you don't want that 3 there. You don't want this 3 to be here because this didn't have a 3 out here, did it? There's a 3 inside, but there's not a 3 on the outside. So you would say, okay, I need to kill off a 3. How do I kill off a 3? I need to put a 1/3 in front, right? Okay. Does that kind of make sense? Okay, this is not the way we're going to do it, but I want you to see that there's more involved when this is not your basic just cosine x. It's cosine of something else. There's more involved than just the antiderivative of cosine and sine, all right? So here's what we're going to do in order to handle this. We're going to introduce this new technique called U substitution. And I refer to this as U sub. And I think a lot of Cal 2 students will say that. They call it, oh yeah, U sub. All right, so U sub. So here's the way U sub works. And it's weird when you first see it, okay? But you'll hopefully catch on after a few examples, maybe a few hundred, but it'll require more than one, okay? All right, so here's the basic idea. What you're going to do is you're going to look at the integrand. Okay, you're going to look at it. Okay, take a look at it. And then what you're going to do is, excuse me, try to find something in the integrand and its derivative must also appear in the integrand. This marker's too loud. All right, just copy it down, then I'll go through examples and explain what's happening here. But there's a little catch at the end of this. It's okay if the derivative is off by a constant. I need more. Second point here. Derivative can't be in denominator or trapped. Again, just write it down. We'll explain with examples. So we're going to look in the integrand. We're going to try and find something. And we also want to see the derivative of that something in the integrand also. It's okay if that derivative that we see in there is off by a constant, but the derivative that we see can't be in the denominator or trapped. Okay, I'm going to start with a whole new example, all right? We'll get back to this one, but let me just start with a whole new example. Ooh, good one. Let's stick with let's put out here in the front 2x times cosine x squared dx. All right, we're trying to find the antiderivative of 2 times x times cosine of x squared, right? That's what we're trying to find the antiderivative of. All right, so first thing you do is you think about, okay, is there something from Cal 1 that you know when you take the derivative of it, you get that? And your answer should immediately be no, all right? You're not going to be able to just come up with something and just be like, oh yeah, derivative of this is that thing, all right? Now, Do you see something? Do you all agree with me? That you look at that and you're like, oh yeah, it's not obvious what you take the derivative of to get this? Is that fair? Okay, so the only thing we really know how to do at this point, if it's not something we recognize, is this method. And in Cal 2, there's like 5 or 6 methods. All right, so this is the very first one. All right, so what we're going to do is we're going to look at it, and we're going to look within the integrand, and we're going to ask ourselves, do we see something and its derivative? So do you all see it? X squared is our something, and do you see its derivative up here? 2x, there it is, right? So this is our something. And this is the derivative of that something. Agree? Is the derivative that we see up there off by a constant? Well, no, it's not, because the derivative of x squared is 2x. That's exactly the derivative, right? It's exactly the derivative. Derivative of this is this. But had this been 3x, we would still be okay. It's okay if this is off by a constant. Does that make sense? Okay. But we don't have to worry about that here. Now, the derivative can't be in the denominator or trapped. So is this 2x in the denominator? Well, there is no denominator, right? Is it trapped? So what I mean by trapped is the 2x inside of like a square root, or is it inside of some other function? Like, is it inside of a cosine or a sine or a natural log? Is it trapped inside something? No, it's not. It's just multiplied here, right? It's just multiplied. So it's not trapped. So we basically have thumbs up on both of these things, right? So if we have this, then what we're going to do, the next step from here would be to let u be equal to the something. All right? So I'm just carrying on the steps over here. So over here in the problem, what I'm going to do is I'm going to let u be equal to, and notice I'm doing it to the side over here. I'm doing that on purpose. Let u be equal to what? X squared. Okay. So I'm letting u be equal to the something. Now, what we're going to do every single time you do u substitution, as soon as you let u be equal to whatever you want it to be, you're going to differentiate both sides implicitly with respect to x. So what is the derivative of u with respect to x? Du dx. Right? And what is the derivative of the right side with respect to x? Just 2x, right? Now, after you take the derivative with respect to x on both sides, you're going to isolate the du, basically getting rid of dx on this side, so you're going to multiply both sides by dx. Okay? Now you get to play a game where you try and match things. Right? So let me use a red here. Everywhere I see an x squared, I'm going to replace it with a u. So I'm going to replace that with the u. Okay? Then, do you see this 2x dx? Do you see that? Isn't that 2x dx? Because remember, this is multiplication, isn't it? So if I wanted to, I could rewrite this problem like this. Because this is all multiplication. This times that, right? So I just slide that to the back. And do you agree that this now, this piece right here, can be replaced with what? Du. And this piece right here is going to be replaced with u. And then won't the entire expression switch from x's to u's, right? We have made a substitution. We've replaced our x's with u's. So now I do that. Pardon? You're okay with how I got this, right? Like just doing this? And then what I did is I realized I have 2x dx if I slide that 2x to the back like this, and this match, right? They're exactly the same. So what I'm going to do on my next line is I'm going to rewrite this. I want the antiderivative of cosine of what? X squared, but x squared is u, right? Cosine of u times, not 2x dx, what? Du. And now this problem is just like if I would ask you today, walking into class, what's the antiderivative of cosine x? Everyone would have said sine x plus c, right? But if now I say, what's the antiderivative of cosine of u? You're going to say sine of u plus c, right? So see, now we've gotten it down to something we know how to take the antiderivative of. So what is the antiderivative? Sine of u, right? Sine of u plus c. Now this can't be our answer because our original integral, right? Our original integral had x's in it and our answer has u's in it. So I've got to switch back now to x's. So I'm just going to replace u with x squared. Okay? So this becomes sine of x squared plus c. And that's what I box. And how do I check to see if it's correct? Take the derivative, right? So what would the derivative, and we have to know chain rule here, right? So the derivative of sine of this would be cosine of it, right? Cosine of it times the derivative of this, which is 2x, which is that, right? So it works.
So the du is like dx?
Pardon?
The du?
The du,
Does it work like
when you
this?
do this step,
Yes.
yep, it's
That's
gone.
what he said in dx.
Yep, the du is now going to become the c. Yeah, if you want, that's what it's going to do. Okay? But this is actually very important in the process now because we replaced 2x dx, right? We replaced it. If that was never there, then this wouldn't make any sense. I like to think of dx as being, do you remember that story I told you about that girl I met in that club when I was like, what's derivative of x? And she said, with respect to what variable? Right? Most people are going to say 1. This is really like a 1. Okay? This is really like the derivative of x is 1. But we're actually going to write it down as dx because if we ever do a substitution, then like the derivative of u here, du, is not 1. It's this, right? So it's just to keep track. Even though it's a 1 right now up here, it's to help us keep track of everything as we go backwards with the substitution. Shall we do another? All right, let me just slightly tweak this. I'm going to erase all this. I need the space.
Should the constant value c always be by itself? Like just c on
As opposed to
like for example, if we needed like 2c.
2c and c would be equivalent because they're both constants. C is an arbitrary value, so twice that is still an arbitrary value. Right. All right, how about this one? Sorry. I'm getting ahead of myself. I'm sticking with this cosine thing just because I don't want to go too crazy here yet. All right, so you look at that, and when you look at it, I mean, right off the bat, you should be like, I don't know what the antiderivative of that is from Cal 1. Like, it's not. Okay, so do we see something in its derivative? So x to the fourth, what's the derivative of x to the fourth? Derivative of x to the fourth is 4x cubed. Do we have 4x cubed? We have 1/4 x cubed. So it's not exactly the same. It has x cubed, but it's 1/4 instead of 4, right? Is that okay or not? Yes. That's okay. You can be off by a constant. So the 1/4 being there is not a problem, all right? Now, so what should my u be then? What was this something?
X to the fourth.
X to the fourth? Yes? How about x to the fourth plus 1?
It'll work.
It'll still work, right?
Yeah.
So which one should we use? X to the fourth or x to the fourth plus 1?
Plus 1.
Let's grab the 1 also. And the reason why is because if you don't, then you're going to probably have to do another substitution after you do the first substitution. Because then inside you're not going to have u, you're going to have, like if you call this u, then when you do your substitution, this is going to become cosine of u plus 1, which means you're going to have to do another substitution to make it look like cosine of, I don't know, maybe w or something. So the trick here is to try and grab as much as you can without grabbing too much. Right? So I'm going to let u be x to the fourth plus 1. All right, now take derivative both sides implicitly with respect to x. So du dx is equal to 4x cubed, right? The next step should always be to isolate the du, so get dx to the other side. Brain is not working. There's going to come a point soon, meaning today, where I start skipping this step and I go straight to this step. I'm just going to write, okay, du, and then I'm going to write derivative of this, and I'm just going to slap a dx to the back of it, just to save us one step. All right, so let's see what we've got. I'm going to come in here, I'm going to be able to replace x to the fourth plus 1, right? That right there is going to be replaced with u. So I'll have a cosine u there. Now I need to account for all this other stuff. So do you see here that I have x cubed, 1/4 x cubed dx? I don't have that here, do I? I don't have that here. So just watch me do this first, all right? Watch me do this first and see what you think. Okay, so what did I do there? I just divided both sides by 4, right? I divided both sides of this by 4. This has nothing to do with this 1/4. I just decided to divide both sides by 4. And the reason why I did that is because now, see this x cubed dx? That matches up with this x cubed dx. Remember, I can move that x cubed over here, couldn't I? Okay? So with that said, let's see if we can just rewrite the whole integral, all right? So this integral becomes, all right, did I do anything with the 1/4? I didn't, right? It's still there. So I'm going to write 1/4. Okay, let's skip over this x cubed for a minute. Let's go to this piece. What am I going to write to replace this? Cosine of u, right? All right. Now, I still have not done this stuff in purple. What is x cubed dx going to be replaced with? Is it going to be replaced with 1/4 du. 1/4 du. So I'm just going to slap that to the back. Okay, so again, this 1/4 du is replacing that piece and that piece, right? This u is that, and then the 1/4 just came down, right? That makes sense? So now we have this. 1/4 times 1/4 is 1/16 cosine u du. I'm not going to put the u in parentheses this time. It's the same thing. And now, do you know the antiderivative of cosine of u? Yeah, sine of u, right? Plus c. But what about the 1/16? Remember from last class, they come for the ride, right? Constants come for the ride. So this is going to be 1/16 sine of u plus c. And what is u? X to the fourth plus 1. So that should be our final answer here. 1/16 sine of x to the fourth plus 1 plus c, box it up. And then how would we check it? If we wanted to check it. Take the derivative, right? So if I take derivative of this to check it, 1/16 comes for the ride. Derivative of sine of something is cosine of it. Times chain rule, derivative of what's inside. 4x cubed. This 4 and this 16 reduce. And I get a 1/4 cosine of x to the 4th plus 1 times x cubed, which is the original integrand, right? All right, does that make sense? You ready for something a little more difficult? Yeah? Okay, how about this? Secant squared of sine x cosine x dx. Secant squared of, right? Secant squared of sine x times cosine x dx. So yeah, there's nothing we have from Cal 1 that you just go, oh yeah, that's a derivative of blah, right? So do you see something in its derivative? Okay, the derivative of sine of x is cosine x. So if I were to let that be u, the derivative of it is cosine x, right? Now, what about cosine x? Could you let u be cosine x? Yeah, so like what if we let u be cosine x? What's the derivative of that? Negative sine x. Do we have a negative sine x? We have a sine x, but it's not negative. But that would be okay, right? The fact that it's positive, we'd be off by a constant, but it's trapped, right? So if I let u be cosine x, the derivative of it, sine x, negative sine x, is in here trapped inside the secant squared. I do not want that. The other way around works. If I let u be sine x, the derivative of it, cosine x, is outside, not trapped. Do you all see the difference? Okay, so let's let u be sine x. du equals cosine x dx. So see, I skipped that step. I just went straight to this. And now we try and play this little matching game. Right? I'm going to replace my sine x here. That's going to be replaced with u, right? So the only thing that I really need to worry about, because this will be secant squared u, right, is to try and figure out what cosine x dx is going to be. But it's right there, right? There's really no work to be done. That matches up exactly right now. Okay? So now this integral antiderivative becomes secant squared of u du. Now at this point, you look at that and hopefully you recognize that as the derivative of something. That's the derivative of tangent. So this is going to be tangent of u, right, plus a constant. That's using what we know from Cal 1. Derivative of tangent is secant squared. And now final step is to replace the u with sine of x. So tangent of sine x plus c, box it up. And then you could check it by taking its derivative and using the chain rule. Okay? All right. Okay. Yeah, okay. That looks bad, doesn't it? So we definitely don't know something from Cal 1 that we can just say, oh yeah, that's that, right? So the only other thing we have is U substitution. So just a little side note here. Part of what I think makes Cal 2 hard is, depending on who you take it with, a lot of times your first test is just over all of the techniques of integration. So you go through all the 5 different techniques or 6 techniques. And so when you get a test and you're given a problem, it doesn't tell you, you don't know what technique to use. Like, so you don't know if this is going to be just a basic Cal 1 thing. You don't know if it's going to be U substitution, what I'm showing you, if it's going to be integration by parts, if it's going to be trig sub, or partial fractions. Like, you have these 6 different things, and that's what makes Cal 2 very difficult. Not to mention that it's not, I mean, can you already see that this is not as straightforward as taking a derivative? Like, product rule is very robotic, right? I mean, there's a formula for the product rule. There's no like general formula for going backwards. It's like you're going to try something, see if it works, if you even see it. So do you all see it here?
Yeah. So
What do you see?
1 over x.
The derivative of, so you're saying U should be natural log of x? Is that what you're saying? U should be natural log of x?
That's what I'm thinking.
Because its derivative is what?
Well, 1 over x.
1 over x. And we kind of have that, don't we?
Over 3x.
We kind of have that. So let me rewrite this. It might be easier if we first rewrite this. Let me see. Okay, do you all agree that that's the same problem?
Yep.
Okay, it's just me using algebra, right? The 3 down here is pulled it out. The x down here I pulled it out as a 1 over x. And then natural log of x cubed on the top, I just put it like that. By the way, can I pull this 3 out? No, the 3 is on the entire natural log, and so powers don't come out. If the 3 were on the x, then I could pull it out, okay? So I can't pull that 3 out. Do you all agree that that's true? Is it easier now to see that U should be natural log of x? If U is natural log of x, that's our something. Our derivative is what? 1 over x, right? Now, what if you had put the 3 under here and put 1 over 3x instead? Well, you would have been off by a constant, wouldn't you? You just would have been off by a constant. No big deal. You still would have had 1 over x with the 3 there. Who cares? But I've peeled the 1/3 off to the front so it doesn't interfere with the 1 over x. All right, so now we let U be equal to natural log x. Then du is equal to 1 over x what? Dx. Don't forget to write that dx. And now you get to play your little matching game. See, the matching game is kind of fun. Natural log of x right there. That's going to be replaced with u. And then everywhere I see 1 over x dx, that's right here, I'm going to replace that with du. So this thing is going to be my du. And then the 1/3 out front, I just bring it with me, right? Any questions? So this is going to become integral 1/3. 1/3 what? U cubed. U cubed. Right? So this right here, the natural log is our u, but we still have to cube it. So u cubed, and then this is just du. Now, can you find the antiderivative of 1/3 u cubed? That's just power rule. That's from last class. It's just we're using u instead of x. So the 1/3 will just come with us on, for the ride. And then it's going to be, let's see, u to the 4th over 4. I'm going to write it as 1/4 u to the 4th plus c. So this right here is the antiderivative of u cubed, but I just slapped that 1/3 that was out there. I slapped it on. And cleaning this up, this becomes 1/12 multiplying across. U to the 4th. What's u though? U is ln x, right? So this becomes natural log of x to the 4th plus c. Fun or no? No? Interesting. Ready for more? All right, so you look at that and you start thinking from Cal 1, you know, if you know anything. And while you're looking at that, I'm going to write this down. It's not the same problem, right? Those are two different problems. Could you do this one? How would you do this one? Split it up into two different pieces. You would do 1 over this, right? So you'd go 1 over 5x. And then plus x to the 4th over this, right? So this would become x to the 4th. I'll reduce on the next step, but it would be like that, right? That's what that would become. And then could you find the antiderivative of both of those? You should be able to use power rule here. This would become 1/5 times 1 over x plus this one would be 1/5 times x cubed. Do y'all see what I'm doing here? Rewriting this as this, rewriting this as this, and then now you can just do antiderivative of that, which is 1/5 natural log x, and then antiderivative of this, which would be 1/5 times 1/4 x to the 4th. So you could do them separately, right? That's how we would do this. We can't do that here. Why? You can't do this over this, that over that. That's not the way fractions work, right? We do it that way. But if you have two terms here and one here, you can't split it. Okay, let me write down an answer, and don't write this down. But I want you to tell me what this student did. So what did that student do? Power rule. They just said, okay, I can find the antiderivative of 5x by just bringing the 5 for the ride. What's the antiderivative of x? 1/2 x squared. So put those together. And then antiderivative of x. Oh, sorry. This should have been x. Antiderivative of 1, which is x. And then antiderivative of that, which is that. And I understand what this student did, but it's completely wrong. Because if you differentiate this, take derivative, you have to do quotient rule. You won't get back that, I promise. All right? In fact, if it were that easy to go from here to here like that, then Cal 2 would not be hard. This is what makes Cal 2 hard, is you can't undo a quotient or a product easily. You can undo addition and subtraction easily by doing them separately, but whenever you have a product or quotient, the reverse of derivative, antiderivative, is hard. All right, so it's not something we recognize. It's not something like that. So the only thing we have on our plate is substitution. So you got to see something in its derivative. Y'all just let me know. I'm just kidding. So in Cal 2, you're going to have to get used to failing, all right? At trying and then trying again, crumbling up your piece of paper and starting over, all right? There's sayings about, you have to fail, failing is learning and all this stuff. And it's true. In Cal 2, the only way you learn is to try, but you can't be like I was in grade school playing baseball. You can't be like me. I'd go up to bat in playing grade school. I get hit by the ball because I was a left-hander. I'd always get hit by the ball, so I just stopped trying. And I just didn't want to play. Can't be like that. You got to be willing to get up here, get hit by the ball, take a swing, strike out, go sit down. Yes?
Can you separate the 5 and the x?
Yeah, you can peel this 5 out. In fact, that 5 could come out here, and we could even place it out here, which I will start doing later. But yeah, because of multiplication, you can. Yes?
And then the derivative of x.
Okay, good. So let's go with this, all right? I'm going to put it over here because this is just us thinking, all right? Let u be, what did you say, x? Yes? Okay, so the derivative of this would be 1 dx, correct? 1 dx. You always have to have the dx here, always, because we'd always have du dx, and then the dx would come over here. So do we have a 1? We do, right? But what's wrong with the 1? It's in the denominator. Okay? Can't be in the denominator.
So that's the case of being trapped.
This is either being in denominator or trapped. You could say it's trapped in the denominator if you want. Yes?
Well, could you pull it out and say 1 over 1 plus x to the 4th times 5x?
Absolutely, you can do that.
And that x would go 1 up in the numerator.
Hold on. You're just saying to do this? Could I do that? Yes?
Yeah. And then you have a 1 in the numerator.
Okay. I agree. We do that. We have a 1 in the numerator. You want me to keep going? I'll keep going.
The denominator.
So no, because this is very important. This is good. You're going to learn something from this. So let's stick with that, okay? And what we're going to do is we're going to try and match things up, okay? Everywhere we see x, we're going to be replacing it with what? U. Everywhere I see 1 dx, I replace it with what? Du. Okay, so let's see where that is. All right, this right here is going to get replaced with u. This right here is going to be replaced with u. And then 1 dx. Remember, that 1 could really, it's here, but it's also here, right? So that right there is going to be replaced with du. That's going to be replaced with u, and that's going to be replaced with u. Right? Let's see what our new integral looks like. It's the same integral. It's 1 over 1 plus u to the 4th times 5 u, but that and that together was du. So you have the same integral. So the lesson is, and this is a good lesson to learn right now, and I'm glad you took a swing, all right? Don't ever let your substitution be u equals x. Because what you'll wind up doing is rewriting the whole problem in terms of u. So it'll be the same exact problem, but it'll just be with u's instead of x's, okay? All right, so can you what?
Just let u be the denominator.
Here we go. Ready? Let u be the denominator. Okay. Let's just follow the procedure then. Derivative of this is what? 4x cubed dx. All right, do we have a 4x cubed, or really do we have an x cubed dx? Remember, this is already taken care of, right? This right here is u. That whole thing is u. All I have left up here is this, right? I don't have an x cubed, right? I don't. And you can't do anything like this. You can't come over here and like take the cube root on both sides, because, imagine if I did that. If I took the cube root over here and cube root over here, then I'm going to be plugging in a cube root of du. And I can't have cube root of du. It just has to be du. That's it. Maybe maybe 5 du or a number in front of it, but it can't be like du trapped inside some function. So do you want me to continue, or do you see the trouble here, that it's not working? You see that?
Wait,
Can you let the u be the entire, like, be it numerator, and can you let u...
Could you be the whole thing?
Like a fraction.
Like the whole thing?
No, it's like, I'm saying, like, the next trick thing I'm gonna try is, if I just separate them out, maybe I can do like 5 times this.
So hold on, are you giving up on that?
Well, you're saying that you can't, you already said that you can't do it.
It just says it doesn't look like it's going to work.
Oh,
But are you giving up on it?
no.
Hmm?
That's the case, no.
I'm not telling you to do it or not to do it. I'm just saying, what do you want me to do? Do you want me to give up on it? Because it looks like you're thinking of a different idea now.
Just continue with that.
Continue? Okay, so if I continue, what do I do? I mean, I can replace this right here with u, right? But I've got to somehow I just don't see how we're going to get x cubed to x. Al, is that right? Yes?
Again, taking a swing.
Okay, take a swing.
Divide by 4x squared.
Pardon?
Divide by 4x squared.
Okay, so all right, let's try that. How about that? Let's do that. I like this idea. How about if we take this equation, we divide both sides by 4x squared? Seem reasonable? What would this side become? X dx. And this side would become du over 4x squared. Okay, so Al, what you've done is you've created the x dx. Yes? So I will be able to replace x dx with, right here, this x dx gets replaced with du over 4x squared, right? So let me try and rewrite this now. Integral. This 5 is still there, right? Okay. Over, this is u. And then this x dx is being replaced with what? Du over 4x squared. Now, what's wrong with this? You've got two variables in there. You've got u and x still mixed together. Your goal is to get from x's to u's and only u's. So good, this is a good, I mean, you created the x dx, but the problem was the other side had x's in it, right? Pitching a no-hitter. Yes?
So we can split x to the fourth into x squared to the squared.
Ah. You can do what? You can do this and treat that as what?
X squared to the squared.
X squared squared? Okay, this seems like craziness, but let's see here. Okay, I'm gonna go with this.
Then
What do you want me to do?
you let u be x squared.
Let u be x squared. All right. So now next step here would be du is 2x dx, right? Do I have a 2x dx there? So let me see. What you're saying so far is that this, just that, will be replaced with u, right? And then you also have this x dx, right? There's a 5 here, but I'm off by a constant, right? So what I did last time here is I just multiplied. I scaled both sides, right, to make this x dx. And do you see that this right here matches up with this right here in red? Okay, so looking promising here. So what would this integral become if I switch it now? Still have 5 over 1 plus u squared times, okay, this x dx becomes what? 1/2 du. All right, now I'm going to go one more step.